Okay, let us see an example. Um, this example is pretty interesting because it is very similar to what happens in real life. So the problem says that there are two cables of the same gauge attached to a transmission tower at point B. So first of all, gauge is a term. It refers to the thickness of the wire diameter, and it's because the gauge it's by code the gauge refers to how much amps or electric current or amperage can go through a cable or a wire. So this is 90 meters, this is 60 meters, so the distances are pretty long. Therefore, I'm thinking that this is the type of cable or wire that you see when you drive through the highway. They carry a lot of voltage and current. They carry up to, I've seen cases where they're up to 19,000 volts. And if they're the ones in your neighborhood, they could be as low as 480 volts. So you have all sorts of voltages going to through cables, and if they're the ones that carry the high power, they go to a substation. You see them all over the place and by the road where they stepped down using transformers. But the cool thing about this example is that it's somewhat related or similar to what happens in real life. Of course, since you have a lot of voltage and current, the electric field and the magnetic field and the magnetic flux that go through and around the cables is pretty high, is very large. So there are other norms that engineers have to follow to make sure that they put the distances and the right angles and the right insulators, etc. But just from a perspective of the tension and the geometry, this is a pretty good example. So they're asking to find the h, the distance h, this guy right here, with respect to the datum, and the maximum tension in each cable. So the maximum tension is really the tension at which h is whatever this h is that we find, and this is 3 meters, and that the cables are at 90 and 60 meters. What tension would this make this geometry happen? So this tension is the one that will make this system be static and stable. So what is the tension and what is H? They're telling us the density of the wire is zero point 0.4 kilograms per meter. And yeah, we have everything else that we need. So I'm gonna get rid of this electric magnetic field stuff because we're gonna talk about forces, mechanical forces, not electric forces. So from a mechanical standpoint, the first thing we want to know is, remember that we talked about a capital W, which is the weight of the cable, and that is little w times the amount of distance that we need there to run the cable. Of course, that will basically mean that we have 0.4 kilograms per meter times 90 meters. So meters go with meters. This is for W1, and W2 is equal to the same type of wire, but is going to be X2. So this is going to be 0.4 kilograms per meter times 60 meters, and we'll compute that in a second. Okay, so that's the first thing. The second thing is we're going to do a body diagram of the cable. So remember that we choose the bottom point where X is going to be a component in completely horizontal, and that looks like so. So this is the cable, exaggerating the curvature. We're going to choose a point right here. Let's call that point, I don't know, point P. and we have another point right here, which is my point B. So obviously there's a tangential force, which is this tension, and there's a x force, tangent force as well, this curvature, that is my TPX. The wire of the cable has weight, W, and that is precisely how we form the force of this parallelogram, or in this case it's a triangle. This is how we find or form the triangle. So we have a hypotenuse, adjacent force, and a vertical force. So the direction here is W, the direction right here is TPX, and this is capital T. Okay, so we have more information though. We have that this W right here is located at X. This is at X over 2. So we know that complete length is 90 and for the second case is 60. And also we know that this right here is a distance B, right? This whole distance right here is X to point B. All right, this W is capital W, so this is the case for each part of the cable. And then with this, we can do summation of moments as we did before at point B. So we can do, let's do summation of moments at point B equals 0. Let's take counterclockwise positive. And in that case, we have Tx or Tpx is doing a clockwise moment with respect to B. So that is going to be negative times a distance of YB, the vertical distance, and then this W is going to do a positive moment at a distance of X, the distance of X over 2, XB over 2. This is equal to 0. So really what this means is that TPX is equal to W, which W is WX. So W times, this is capital W, this is little w, X squared over 2YB. In fact, we could have just used the formula that we derived. So when you just use this, you save a bunch of time, but this is once again how you do it. So this value right here is this value right here. Okay, so if we take the first case and we talk about for point A, B, or for not point, but cable, for cable AB, we have that XB is X is 90 divided by 2. It is equal to 45 meters. Therefore, TPX is equal to the weight, which we do know, times X, which is 45, that's squared, divided by 2Y. But it turns out that Y is this H right here. So that is exactly what they want to find, H. Okay, so in that case, we can actually find this, but we don't need to right now because there are two cables and they're asking us for the tension. So we can find the tensions at the same time. So let's put this as equation 1. Let's do the same thing for cable BC. So for cable BC, what we have is that 60 divided by 2, that's point C, right? Yes, B to C. This is 60 divided by 2, which is equal to 30 meters. And then we do the same thing. So T, P, let's call this point Q. It will be the same concept, but from a point Q to C. This is going to be Q and C, and there's a new H or a new YB, and this is XC. XC is 30. XC. All right, so T at point Q, the horizontal component, and this is the tension, and there's a W2. So the force parallelogram looks like this: W2, T, and TQX. So TQX is equal to the same cable, but the distance, which is 30 divided 30 squared, and then here we have divided by 2 y, and that is 3. 2 times 3. Okay, so if you notice, they're telling us the horizontal component of the resultant force expected at B is to be 0. So really what they want to do is that tell us is that this tension and that tension is the same. That's how this is designed. If it's not the same, then this thing will be bending one way or the other, and you have extra stress, and it's not good. So that's why I didn't want to cancel out W and find it, because what we want to do is we want to say that TPX is equal to TQX, right? So if you look at the diagram, we're saying that whatever tension we have here has to be the same tension that we have here, and just make that H whatever that has to be to make those tensions the same. You start with one design, one line, and then everything else you can equate to the tension here. You keep finding the tensions throughout your system so that every tension is based on the tension that you start from. You don't want to have cables with different tensions, because that's not good for the electrical aspect of it either. What this means though is that we have to bring equation 1 and equation 2, which we're going to name this one equation 2. So bring that equal to that. So here we say that W times 45 squared divided by 2H is equal to equation 2, which we saw it right here, W 30 squared divided by 2 times 3. So I think we can solve this pretty easy. This is going to be 45 times 45 divided to H equals 30 times 30 divided by 6. So let's see what we can do here. This is going to be H times 30 times 30. You can use a calculator if you want. It will be way easier. H 30 times 30 is equal to 6 times 45 times 45. Okay, in that case, H is equal to 6 times 45 times 45 divided by 30 times 30, and this is equal to 1, 5, and this is equal to what multiplied by 5 is 45. So we can cancel this one out. 9 times 45 divided by 30, right? So 9 times 45 divided by 30. Well, actually, we can cancel this more because this is 5, this is 5. So this is 9 times this divided by 5 is 9, and this divided by 5 is 6, and h is equal to, this is 3 and this is 2. Alright, so this means that we have 27 divided by 2. What is that equal to? 27 divided by 2. Well, let's do calculator first. So we have 27 divided by 2. We have 13.5. All right. 13.5. That is way bigger than I thought. That is way bigger than I thought. Do we have an error here somewhere? Do we have an error here somewhere? All right, so 6 times 45 times 45 equals 12,150. All right, and 30 times 30. 30 times 30 equals 900. So 12,150 divided by 900 equals 13.5. So why is that distance so long if it's only increasing 30 meters? Let me check. I have something wrong here. That shouldn't be more than twice. Because this is 3 meters. How is that going to be 13 if it only increased 50%? Let me see my equation here. My equation tells me that W times 45 squared divided by 2H is equal to W 30 squared 2 times 3. This is 6. So 30 times 30 times H, yep, 45 times 45 times 6. 1, 5. Oh, wait a second. This is why, because I dropped the 5 here. All right. Did I? Let me see. I don't think I did. So this is 45 times 45 divided by 5 times 30. Oh, I didn't. I said that this is 1 and this is 9. 9 times 5, 45. So this is 9 times 45 divided by 30. And this is 9, and this is 6 times 5 is 30. 18, no, sorry, 91 divided by 6. 9 times 9 equals 81. And then divided by 6. 13.5. I guess it must be 13.5. But that's way larger than I was expecting. Much larger. Alright, let's go ahead and carry on. So If we go ahead and solve for this guy, we get 13.5. 13.5. Y is 13.5. Okay, so H, let's go ahead over here and do H is equal 13.5 meters. All right. So that is not as intuitive as I thought. This one is only 3 meters, and this one is 13.5. Okay. All right, so it is what it is. I don't think I have an error, and if I do, please let me know. All right, so now they're asking us to find the maximum tension of the cable. So part B. So we're needing to find the maximum T, which is the T that will make everything static. So we know that in that case, we need to do this computation after all. So what is this number? 0.4 times 90. 0.4 times 90 equals 36. So this is 36 newtons per meter. 90 meters. Oh, wait a second. Yeah. So we have 30. So we have 0.4 times 90 is 36 kilograms. And right here we have 60 times 0.4. 60 times 0.4. This is 24 kilograms. So we actually need to multiply times gravity times 9.81 times 9.80. So let's do this over here. Let's do that over there. So 36 and 24. So force for W1 is equal to 36 kilograms times 9.81 meters per second squared, and force for W2 is 24 kilograms times 9.81 meters second squared. All right, so what is 36 times 9.81? 36 times 9.81. 353.16. So this is 353 newtons, and this is 24 times 9.81. This is 235.44. 235.44. All right. So what we can do now is go back to our equation here and find what is our tension. So with this equation right here, we can find the tension. So for tension at Qx, we have the one for point P, which is 235.5, let's say, 235.5 times 30 squared divided by 6. And this is in meters. Let's go ahead and check this equation very quick. So these units are, let's check right here. So this is meters, this is Newton, this is meters. So TQX has units of newtons times meter squared divided by meter. So this is Newton per meter. So if you notice, we have a problem, because if we keep doing this, we're gonna have a unit of moment. But indeed, this equation is to find force. So that means that we need to have newtons over meter here, so that we cancel. In that case, good thing that we checked the equation, because this point right here, we have we have an error here. This is not what we need to do. This is not what we need to do. It's not going to be a force that way. It's going to be the density times the gravity, 9.81 meters per second squared, times 9.81 meters per second squared. Or that number below, you could have divided by the meters, with 90 meters. So this one is going to be easier. So 0.4 times 981. So 9.81 times 0.4, that is 3.92 newtons per meter. So that is the distributed load, 3.9 newtons per meter. And the other one is 0.4 to, well, the other one is going to be the same case. Excellent. So we don't need to do this part anymore. We don't need to do this part anymore, because it's going to be the same distributed load, and then we multiply with the meters here is going to be fixed. It's going to be what we need to do. So 3.9 newtons per meter. So in this case, what we need to do is TQX is equal, here's going to have the 30 meters right there. So 3.9 newtons per meter times 30 meters squared divided by 2.2 times 3 is 6 meters. So meters and meters cancel with that. We have units of newtons. So let's do that. 30 times 30. 30 times 30 times 3.924 divided by 6. It's 588.6 newtons. So that is that force. This is equal to 588.6 newtons. That is the point, the tension X. This force right here. And in that case, what we need to do is compute this guy right here. So this we know is this. This is equal to, let's go over here. this is equal to W2 is equal to 3.92 newtons per meter times 30 meters. So W2 is equal to 30 times 3.92 newtons. That is 117.6. But wait a second, what distance do I need to use? Yeah, so 117.6 newtons. So we have that and that. So what we can do is that we can compute the total force doing square root. So the tension T is square root of 588 squared plus 117 squared, and I'm going to need a better calculator for that. So I don't think this calculator will give me square. Oh yeah, it will. Okay, so what we can do is, let's do that again. So 588 times 588 equals 35,744. Okay, and 117 times 117 equals 13,699 plus 345,744 equals, and then square root of that is 599.5. So this is equal to 600 newtons. So this tension right here is 600 newtons. Okay, so we can do exactly the same thing for the first part of the equation. So this is W1, which is equal to 3.92 newtons per meter times 45 meters. This is because it's only half. This is equal to 3.92 times 45. 3.92 times 45 equals 176.5. 176.5 newtons. All right, so we have this one. We have to find this one, and we have TPX, do we not? We do not. We have to compute it. So for that, we use this guy. So TPX is equal to W times 45 squared over 2 times H. And in that case, we can do, well, you just put this in the calculator. So this is 176.5 times, wait a second, this is, remember, this is the part that I got confused earlier. So this is in meters, and this is in meters. So this part right here is in Newton meter. So it's 3.92 Newton meter times 45 squared over 2 times 13.5 meters. Okay, so let's do that. 45 times 45 times 3.92 equals 7,938. 7,938, and that has units of 13.50. So let's do this. 13.5 times 2 equals 27. Okay, so 79 38 divided by 27 is 294, and that is units of newtons. 294 newtons. Okay, so we have this one and this one. In that case, we just need to do square root of 294 squared plus 176.5 squared, and this is equal to, let's see if we can do this, 294 times 294 equals 86,436, and then 176.5 times 176.5 is equal to 31,000. Wow, that's pretty big. Plus 86,436, which is also pretty big, almost twice as big. And square root of that is 342. 343 newtons. So if you notice, this force right here is almost 600 newtons, and this one over here is almost 343 newtons. So this is how you solve this problem.